Okay, so let's continue. So we have discussed about the quantization noise. Yeah. Then, so if the quantization noise is uncorrelated with the frequency of the AC input signal, yeah, the biomedical signal in this case, the noise will be spread evenly over the Nyquist bandwidth, which is over the Nyquist bandwidth of frequency sampling divided by 2. Yeah, so uncorrelated means here that the noise come from somewhere else. Yeah, so if that quantization noise is not related with the AC input signal, so we have here the maximum bandwidth of the signal, right? So on based on the Nyquist criteria, Nyquist-Shannon criteria, we have to sample this signal at least fs over 2. But usually it would be better if we sample it with even higher frequency here, frequency sampling. So when so this is the harmonics of the frequency of the signal. Yeah, one multiplied. This is 2 f signal. This is 3 f signal. Yeah. Then the RMS of the quantization noise will be spread evenly. Yeah. After you do fast Fourier transform. Still remember? I hope, yeah, about what fast Fourier transform is. Yeah. If, however, the input signal is locked to a submultiple of the sampling frequency, yeah, the quantization noise will no longer appear uniform, but as harmonics of the fundamental frequency of that quantization noise. Okay. So this is some example of parameters when we have the ADC resolution and what is the effect to the quantization parameter. So if we have the resolution of our ADC is 8 bits, so it means then it can quantize into 256 different levels, right? To the power of 8 means the least significant bit. If the full scale reference voltage is 2.5 volt, yeah, not 10 volt, 2.5 volt, it means then 2.5 volt divided by this 256. So one difference, the difference between two steps is 9.77 millivolt. So the percentage from the full scale, this 9.77 divided by 2.5 multiplied by 100 is equal to this one, 0.391%. Part per million, yeah, basically the same as percentage, but in millions, so 3,906. In dB, the full scale is minus 48. Yeah, from here, yeah, 3,906 from is minus 48 from the full scale value. But when our resolution is increased, let's say it becomes 10, so then the level will be 1024. Then the least significant bit will be 2.44 millivolt. Yeah, so where does it come from? 2.5 volt divided by 1024, 2.44. This is then 0.098% from the full scale, or 977 from the ppm part per million from the full scale, or minus 60 decibel from the full scale. So if we see here, then if we continue further, increasing the resolution bits, the more the resolution, the higher the resolution bits becomes. Yeah, we see that least significant bit becomes smaller. It means it becomes more accurate actually to approximate and approach the analog signal. It becomes smaller. So see here, it becomes 3.8 part per million. It means the higher the resolution because it can approximate better. So no loss value between two steps of the quantization. Okay. Okay. So we mentioned about previously full scale. If the full scale is 2.5, or let's say the full scale is of 10 volt, how do we put the analog input signal into this full scale? So it can be either from 0 to 10, for example. It can also be from -5 to 5, for example, if it is 10 volt. Let's say the full scale is 10 volt. When it is from 0 to the maximum full scale, then we call it as unipolar single-ended. 0 to 10, like this. when the input is only single. It could also be unipolar differential when there is a two input port, input signal. Then we capture the difference between the two. Yeah. One is the positive, the other one is negative input. Yeah. And the full scale is still captured from 0 to that full scale value. Or bipolar single-ended. In this case, is the plus minus. The input voltage will be plus minus full scale divided by 2. Okay, so the total range will still be that full scale value. If it is 10 volt, it means that it will be from -5 to plus 5 volt. If it is bipolar single-ended. Or bipolar differential, when we have two input signal, we calculate the difference between the two input signal. One is positive, the other one is negative of the Vin. Then, or pseudo differential. Yeah, in this case, the full scale is between the negative input of the Vin and positive Vin. Okay, the negative Vin becomes the low DC input. Yeah, so one of the input is not varying, but instead just an offset, becomes an offset. Then the other input is calculated on above that offset. Yeah, not above 0 volt, but above that offset. So this is the various types of input signal definition. So in unipolar or bipolar converter codes, it will be a little bit different than in unipolar. Then the full scale from the input range will be calculated from 0 until the maximum full scales minus 1 least significant bit. Yeah, so until 0, for example, if it is 8, then until 0 until 255 level. Okay, until all ones. If it were offset binary like this, yeah, it will be from the minus full scale until full scale minus 1 least significant bit. Yeah. At the middle, it is 1 and all 0. If it's 2's complement, here between negative of full scale negative 1 least significant bit, so basically this one the same until positive full scale minus 1 least significant bit. Yeah, so like this the conversion. Yeah, from 0 if it is positive value, from 0 until full scale negative 1 least significant bit. If it is negative value, then from negative full scale minus 1 least significant bit until 0. So some factors that affecting the analog to digital converter performance. Yeah, one is offset, of course. Yeah. So when ideally that we don't want any offset. Ideally all the input, if it is the input 0, then the output should also be 0, 0, 0, 0, yeah, in the bit format. If it is, for example, that 2.5 volt, if the full scale is 2.5 volt and the bit is, let's say, 8 bit, then it should be then 255. So the range will be 0 to 255. However, then sometimes or many times we have offset, and the actual value will have some elevated value compared to the ideal value. This becomes the zero error. So the zero error is the value when the input is supposed to be 0, but instead that there's a value of digitized value here in offset. So no gain error. So in zero error becomes an offset error. In gain error, on the other hand, so offset error is 0. However, the sensitivity changes, the gain changes. Ideally, it's straight like this, but with increasing value of the input, the output will deviate with different gradient. So this is called as gain error. The offset, and this is for bipolar range. The previous one for unipolar, yeah, this one is for unipolar. While for bipolar, the offset happens like this. Ideally, the actual is supposed to be, but at 0 there is some gain. So then when the input is 0. Yeah, it's supposed to be 0, but instead when in the actual value, what happened is when the input is 0, there is some value here, which is called as a 0 error. When we gain error, then similar like the unipolar range, but it is start from the negative value. Yeah? There is then deviation from the ideal value. So ideal analog to digital converter code transition are exactly one least significant bit apart. Yeah, so from the code conversion, yeah, from for example between 011 to 100 here, the distance is exactly 1 bit. Yeah, from in this case from if this is 8 bit, yeah, from half of the uh, quarter and 3/8 to the half between 3/8 and half. So this one. So this one is significant bit. For an n-bit analog digital converter, there are two power n codes. Yeah, one least significant bit equals to the full scale divided by 2 power n. For this 3-bit, yeah, this example, it is 3-bit ADC. So one least significant bit equals to 1 volt. So for example, this is the full scale is 1 volt divided by 2 power 3 or 1/8 volt. So each step here is centered on the 8th of the full scale. So uh, 0, 0, 0, 0 is centered on 0. Then 001 is centered on 0.125 volt. Here, this is the center. The annotation. This is 1/8 volt, 0.125 volt. The quarter 0.10 is centered on this 0.25 volt. Then 3/8 quarter, 3/8 volt, or 0.11 will be centered on this 3/8 volt, yeah, or 0.375 volt, etc., etc. Of course, this will change when the full scale range is also changed. When it is not 1 volt instead, but let's say, for example, it is 10, then this will be 3.75 volt. This become 2.5 volt, etc. Yeah. But the idea is each step is centered on the here 8 is because it is 3 bits, yeah, 2 power n. If it is 16, if it is 8-bit, for example, then it will be 1 over 256. Okay. So this is differential nonlinearity. This is one another parameter performance. Differential nonlinearity is the deviation of an actual code width from the ideal one least significant bit code width. One least significant bit code width. Results, yeah, this is one of the error. Yeah? So deviation from the one least significant bit code. Instead of ideally it should be one least significant bit, the width, yeah? But it deviates. Sometimes it becomes longer here. So this is plus half of the LSB in the 011, or then the next level, yeah, the 100 becomes the width is not 1 LSB anymore, but instead it's become negative, become just half LSB. So similarly here, the level of 001 becomes 1.5 LSB, the width. So it results in narrow or wider code widths than ideal and can result in missing codes. Result in additive noise or spurs beyond the effect of quantization. So this is called as the differential nonlinearity. So when you look at datasheet of an ADC, please look also at this DNL parameter. DNR error is measured in LSBS, least significant bit per sampling analysis again. A given ADC will have a typical DNL specification. This pattern will also have an element of randomness to them. This effect of randomness. Then another error is called as the integral nonlinearity. So integral nonlinearity is the deviation of an actual code transition point from its ideal position. The transition point now deviate. on a straight line drawn between the endpoints of the transfer function. Yeah, for example, here the ideally is this dash line. The dash line is the ideal transition code. Yeah, the ideal transition code. However, what happens is this one is the thickened line, the thickened step. So the transition between level shift. For example, here the transition between 001 to 010 supposed to be in the middle between 1/8 and 1/4 of the fault, but it shifts to 1/4 fault to become 010. And for the shift then to 011 at 3/8 of the fault, where it should have been in the middle between 1/4 and 3/8. Then further shift towards uh, to 100 at how many? At the middle between between half and 5/8 fault. So here you see that there is an error of one even up until one LSB error. Yeah, the transition code. So ENL integral nonlinearity error is calculated after offset and gain errors are removed. This will result in additive harmonics and spurs. So when we look here at the coding, so the bow here indicates second order nonlinearity. So while the S, yeah, how the curve look like an S, third order nonlinearity of the error. So when we want to quantify this, the ADC dynamic performance, that was in the previous one as DC performance. Now in the ADC performance, there are some parameters that we can use to quantify the performance. The harmonic distortion, the worst harmonic, total harmonic distortion plus noise, the CNAT, signal to noise and distortion ratio, or S over N plus D, effective number of bits in signal to noise ratio. Yeah, of course, you have studied this time to time. SNR, analog bandwidth, the full power and small signal. Then the spurious free dynamic range, two-tone intermodulation, distortion, noise to power ratio, NPR, and multi-tone power ratio, NPR. So dynamic testing of analog digital converters, for example, is like this. So you put a low phase jitter sine wave source to the bandpass filter. Low phase this is to test the ADC. Low phase jitter with sampling clock source, the clock one. So the clock source for this one was put in the AD converter. Then you put into the FFT analyzer to analyze the spectrum. From there, you know which frequency doesn't belong to the signal, which frequency comes from the noise. Yeah. A fast Fourier transform analyzer is used to measure the dynamic performance. So yeah, this is just a review about fast Fourier transform. So fast Fourier transform converts a signal like this, yeah, like I have explained earlier in the previous chapter, F1 with the harmonics plus 2 F1 plus 3 F1, and then the superposition of these three, this is in a time domain. If we convert that in the frequency domain, it becomes a line, yeah, spectrum, yeah, in the F1 to F1 and 3 F1. If we have then a completely non-periodic signal, then this spectrum becomes more continuous, yeah, in the FFT domain, in the frequency domain. So this is an M-point fast Fourier transform. Yeah, you have this one, the spacing, the signal to noise ratio here, the formula that we have derived earlier in the previous slides. And this dash level is the RMS of quantization noise level. The floor will be 10 log 10 of the M divided by 2. M here is the bit level, the quantization steps. The effective noise floor of an M point FFT is less, this one, than the RMS value, this one, of the quantization noise. Okay. So this is an example of actual FFT plot for a component, yeah, made by analog devices AD7484, which is a 14-bit successive approximation registry analog digital converter sampling at 3 megahertz. So the sampling is 3 mega sampling per second, 3 megahertz, 3 million sampling per second. So the sampling period will be less than 1 microsecond. So about 333 nanoseconds, something like that. So the input frequency is, for example, here 1.013 megahertz. So this is the input frequency. The signal to noise ratio. So this will be the signal, yeah, and the noise will be here. All this random signal, wide spectrum signal. And you see here that the signal to noise ratio is about the lowest one is somewhere here. There's 70 from here, calculated from here, negative this level, 77.7 decibel. Then signal to noise ratio plus D. What is D? I think it's this distortion from the definition. SNR plus D, and this D is distortion, is 77.6 dB. It's a little bit smaller than the SNR. Total harmonic distortion, yeah, THD. Let's see. Total harmonic distortion is minus 95.5 decibel. So this is from the fast Fourier transform. Okay, so we have mentioned this one a little bit, yeah, about Nyquist and bandwidth sampling, Nyquist bandwidth and aliasing in the first hour, or in the second hour, the previous hour. So when two signals that are mixed together, it will produce the sum and difference of the frequency component. When we put two signals together, because some will add to each other, some will subtract. So Nyquist theory, better actually mentioned as Nyquist channel theory, stipulates that the signal frequency F signal must be less than or equal to half the sampling frequency to prevent a condition known as aliasing. So in which the difference component appears within the signal bandwidth of interest. So what appear is not the bandwidth that we want to take, but instead something else. Okay? If this is, so it means that our sampling frequency has to be, so in this case, yeah, the F signal should be less than half of the F sampling. So put it the other way around. So F, it means when we want to adjust our sampling frequency, it has to be larger than or equal to 2 times of the F signal. Okay, so this is the general criteria. So whenever you do measurement experiment, you have to sample 2 times larger than the maximum frequency in the bandwidth of your biomedical signal. Okay, cannot be smaller. Of course, this is the minimum criteria. If you want to have a better performance, yeah, sample more. So 4 times, 6 times, 10 times even. So the more, the better. But of course, then with some drawback that it cannot, that it needs higher energy. So in the frequency domain, if you do FFT, so this is the signal passband. So let's say we have 1 megahertz, the maximum signal of the bandwidth, of the signal bandwidth. So at least we have to sample larger than 2 megahertz, right? Larger than 2 megahertz here. So for example, we sample at 4 megahertz, much larger, so 4 times than the maximum signal of the sample. So sampling minus F sampling minus F signal is 4 minus 1, 3 megahertz. 4 plus 1 is 5 megahertz. The signal frequency is less than half of the sampling frequency. So the sum and difference component fall outside beyond the signal passband. So no problem. It can still reconstruct the original signal. But this is what happens when you do not obey to the Nyquist criteria. The frequency signal here is larger than half of the sampling frequencies. For example, frequency signal is 1 megahertz. You sample only 1.5 megahertz. So this is less than 2 megahertz, right? So f sampling 1.5 minus f signal 1.5 minus 1 is 0.5 megahertz. 1.5 plus 1 megahertz is 2.5 megahertz. So the 0.5 megahertz will become a Lias frequency, which will appear in your reconstructed signal, which actually does not there. So the signal frequency is not there in the original signal. An alias or false image is thus created that falls within the passband of interest. So some additional signal seems to appear. Okay, this is another parameter, the dynamic parameter. SINET is signal to noise and distortion ratio. That's the ratio of DRMS signal amplitude to the mean value of the root sum square RSS of all other spectral components, including harmonics, but excluding DC. Enough effective number of bits, this one, calculated from SINET minus 1.76 dB divided by 6102. Then signal to noise ratio as we have here. Okay, so it's now 12:36. I would like to conclude because we don't have much time, but I will put this slide into the Google Classroom, yeah, so that we can study them. After that, basically, there are some comparison between several algorithms of analog digital conversion. Like this one, successive approximation, like this, approximate the level. If you want to study more detail, there's the advantages of disadvantages. Then there's a pipeline, sub-ranging ADC, etc., etc. Yeah, flash, yeah, the fastest analog digital converter. In first order sigma delta ADC and noise free. For now, I would like to conclude because I want to have a small quiz, yeah, about ADC, and maybe we can continue discussing this ADC in next week, yeah, after the semester break. So first, I would like to